Hi, welcome to Teardown Tuesday. You've seen me mention my HP 3458A 5.5 digit classic bench multimeter before. I've used it in quite a few videos. Well, you may have noticed behind me, I have upgraded. Ta-da! The HP 3457A 6.5 digit multimeter. Big score on eBay. Got it for just over 150 Australian dollars. Fantastic. And it's bang on. Beauty. So I thought we'd crack it open, see what makes it tick. Could be interesting. Let's go. And here it is hooked up to my MV106 transfer voltage standard you've seen in previous videos. Yes, I did violate my don't turn it on, take it apart rule here. I just wanted to tweet some photos and check its performance before I go rip the thing apart today on Teardown Tuesday. And as I said, got it on eBay for like 150 bucks, and it really is a very nice meter. It comes with cow stickers. It's a couple of years out of date, but still, that's not bad at all. We'll have a good close-up view of it. But here it is. I've hooked it up to the MV106. I've set it to 1.00000 volts. I've only got 5 decimal places there. This thing, of course, has 6 decimal places. It's a 6.5 digit meter. In fact, technically, with some averaging in high-res mode, it's capable of 7.5 digits, but you can't get that via the front panel. Apparently, you have to do that via the GPIB remotely. So I do get fairly lucky with these bits of gear on eBay. Absolutely bang on. And of course, if I dial that up 1 digit there, you can see it basically changes by 10 least significant digits. There's a bit of noise there, a bit of fluctuation. We can maybe change the power line cycles or something like that. So anyway, if you want me to do a separate video on using this thing and having a play around with it, let me know. So that's actually not a bad upgrade to the classic HP 3478A. This one's the 3457A, and while it's not a metrology grade multimeter like the famous 3458A, this one's the 57A, don't get confused between the two, it is still a very impressive instrument, and really it's hard to beat for any modern multimeter under $1,000 for example. So, you know, to get this thing for 150 bucks, it's a bargain. So they're certainly worth paying a couple of $100 for if you're in the market for a 6.5 digit multimeter. Its performance is still pretty impressive. It's a 1980s vintage, mid to late 1980s. I'm not sure when this one was actually designed. We'll find out, manufactured. We'll find out when we crack it open by the date codes on the chips and things like that. But yeah, it's still a pretty darn good meter. And of course, it one thing my 3478A doesn't have, it's actually got a microamp range as opposed to milliamps. So there it is. Bang. Look at that. So that's 100 picoamps resolution. Very, very nice bit of kit indeed. And in terms of, you know, basic DC volts accuracy on this thing, like the 24-hour spec on this thing is pretty good. It's down in the order of, you know, 18 ppm or something like that. It's quite a nice bit of kit. So if you can pick one up for a decent price, highly recommend it. Now, while it may look like a big bit of kit sitting on your bench with its big wide front like that, you can see it here compared to the 3478A, which is actually quite deep, and it's actually not that much physically bigger in terms of volume at all, and it's not that much heavier either, which means that you can get shipping usually for quite a reasonable price on these things, even international. But as always, some equipment dealers like to rip you off. I got this thing delivered via DHL for like 70 bucks or something. So for me, it's a worthwhile upgrade just for the DC current range, that microamp range capability. The accuracy of this thing, I won't go into specs on this. If you want me to do a review of it, say, you know, compared to it or something like that, let me know. But yeah, the specs are a little bit better than 3478A, but it has got some additional ranges and all the math capability and stuff like that as well. So a better instrument all round basically, but it has that larger wide form factor, whereas this one is, you know, half hearth rack width. So that's probably its main disadvantage, is that it can take up some additional space on your bench in terms of width, instrument width on your shelving. But apart from that, lovely bit of kit. I love it. And here's the front panel for those playing along at home. DC volts, AC volts, ohms, 2 and 4 wire, DC current, AC current, and frequency measurement as well. And it's got range, auto or manual range selection, display digits, and 6.5 digits. As I said, it is technically capable of 7.5 digits, but getting that to work on the front panel is not possible. I believe you've got to do it via the GPIB, as I said. And if we take a look over here at the configuration buttons, we've got number of power line cycles, so you change the integration time, effectively the update time, and that averages things out for you. It's got auto calibration, auto zero, offset compensation, it's got various triggering capabilities, and it's got an input scanner, an optional input scanner as well, but they're usually a very expensive option to like you can have multiple input channels. As we'll see, there's a slot on the back to actually do that. This one's not configured with that, and you can store and report and recall various configuration settings. And then there's the math capability. Now, unfortunately, this thing doesn't have a huge memory on it. I think it's only 1K or 1.5K or something like that. And I'm not even sure if that is the number of readings. I think it's actually less than that in number of readings, depending on the resolution mode you've got this thing in. So, you might only be able to store a couple of hundred readings, but you can certainly do some usable math and get standard deviations and stuff like that. And of course, we've got proper binding post inputs here. It's got 4-wire input for ohms, and separate current, fused current terminal down here. Now, there's one minor disadvantage compared to the 3458A this one's replacing in my lab here. It's only got the front panel terminals. It doesn't have them duplicated on the back. For my purposes, doesn't matter a rat's ass, but if you've got, wiring these into a production test rack or something like that, that sort of thing could matter. And check it out, it does have calibration stickers on it. Unfortunately, it didn't actually come with a calibration certificate, of course, but it's fairly recent, April 2011. That's not bad at all. I'm certainly not going to complain about that, and that's the reason why it's bang on, because these things, they don't drift much, folks. So really, once you've, if you've got it calibrated a couple of years ago, I was pretty confident. I saw this in the ad and I went, well, that's good enough for me. I'm taking a bit of a risk, but I thought this one would be bang on, and it was. Now, interestingly, it's got analog devices on here, and it seems to have come from, owned by analog devices themselves, and they presumably have their own internal calibration metrology department, which calibrated this thing. And we've got another sticker here telling you what capabilities it's been calibrated over: voltage, current, and resistance. Not a problem. By the way, it was calibrated in 2010. I presume it wasn't calibrated again after that. They probably just let the thing expire. But still, that's pretty recent. It's got a sticker here that says ADPI. I'm going to guess that stands for analog devices, of course, production instruments. So I think this was used in their production environment for manufacturing the analog devices chips. Those automated test racks and something like that, which is why it's in, fairly good nick for its age, really. And it's got a sticker from Test Equipment Depot, but I didn't actually get it from them. I bought it from another eBay dealer, so I don't know whether or not they got it from them or what the deal is there. And it's made in the good old US of A, serial number 2703A. A stands for Made in America, and that's the actual serial number, 11,838. No option 700, just the standard option. And there's the slot for the scanner. As you can, there's no panel on that, didn't come with it, but there's the internal connecting cable for that scanner module. You can pay a couple of $100 for those low EMF relay switch-in modules. So unless you really need that capability, don't worry about it one bit. And it's got GPIB, of course, or HPIB, as they call it, and it's got a voltmeter complete output, so a signal, 5-volt TTL signal when it's actually completed, and an external trigger input as well, standard IEC mains, and switchable from 110 to 240, so not a problem. It doesn't matter where you buy this thing, it's going to be usable. And we've got ourselves a couple of calibration void if seal broken stickers, so we'll go right through those. Lovely, the feeling you get when you crack open the warranty void if steel, calibration void if seal broken sticker. Fantastic. There's no screws on the back of this thing by the looks of it. It looks like it's all sort of done from the bottom here, so I don't know whether or not these screws go all the way through or not. I'm not sure what the deal is there. Yeah, I think they do. I presume that the top, those things don't fall out. Lovely design there, captive screws, so this should, yep, ta-da, just lift straight off. Beautiful, all shielded. That's what you'd expect in a 6.5 digit multimeter. Warning, this panel connected to terminal low, and that's not surprising at all. That internal shield there is connected to your ground. It's not connected to mains earth, it's just connected to the ground on the front panel. And we can verify that by mains earth there, and there we go. There's no connection whatsoever through to the ground terminal because of course it's floating. That's what you'd expect in a multimeter, a bench multimeter like this, but you'll probably find that this power supply shield over here is connected. Yeah, there we go. That one is connected right through, but this one is just internal ground connected for, you know, it's all part of the system ground design to shield all the electronics and ensure there'd be lots of low EMF design in this, lots of star point grounding and stuff like that. And they've deliberately kept it from mains earth as all part of the system grounding functionality to ensure that they get the 6.5 digit performance in this thing. So this grounded top cover here, and when I say grounded, I actually mean ground and not mains earth, as we just saw. It's connected through to the bottom cover down here, which is also separated from mains earth over here. So that one is just the shielding cover for the relay input switching matrix board, which then slots in underneath here. So we should be able to lift that out, and somehow it's got instructions there, should read it. And if we just flip that cover open, it's held on there via this ribbon cable that's attached on, and won't disconnect that unless I absolutely have to. But you know, warning, caution, caution. We've got a gain and flatness control here that warns you that it's input high. That's connected to the input high potential, and there's a V offset adjustment as well. So, but they're the only two adjustments that you can get through this thing. So we should be able to lift this plate off and see the measurement and acquisition board on the bottom here, separate from the power supply and digital display board. Over in this part, you can see the ribbon cables go into the keypad and the LCD and stuff. That's all digital control. There'll be some ROMs under there, microprocessor, but this is all your interesting measurement stuff under here. So it looks like this thing just unlatches. Yeah, there's some sort, there we go, you just push these latches back like that. They're not easy, but unlatch this side first, and then you probably got to unlatch this side over here. Yep, there we go. And that's a nice design. I like that. Ta-da! Look at that. Oh, can see the voltage reference board straight off the bat. And lots of relay switching. Oh, good stuff. And one of the first things I noticed, of course, as part of the system design, keeping these grounds separate, you'll notice that there's only two connecting cables on this thing. One is coming from the transformer over here, so it's got its own transformer tap going over there. That's, of course, isolated due to the transformer. Then it's got its own just linear rectifier and linear regulator over here. And then down in the bottom is the only other connection between the digital board down here and the main signal processing board and ADC board over here. And you'll notice that it looks like there it is, opto isolated. And you can see that opto isolated down in there with the big slot going right through the board. They've even cut this ground earth-in trace over here, because this would be connected. You'd just ruin your system ground if you connected that straight across. So they've actually cut that straight through with the slot, and they've used these opto couplers here, but they're like one of those optocouplers you'd see, you know, like in a photocopier or something like that, where you can actually put something in between like that, and it just cuts off the signal between the two. So that's rather interesting. I would have expected to see a, you know, a basic dip package optocoupler or something like that, but they've gone with that type. So they're doing that to keep the entire ground system separate. This is the grounding point. So if we measured, say, this screw over here, it'd be on the metal shield. That'd be going through to the ground connector on the front panel. And of course, this one over here is connected through to mains earth, as we saw in the measurements before. Now, my idea for why they've chosen that type is it's probably just basic belt and braces engineering. These type are, you know, going to have a larger withstanding voltage, larger isolation voltage, just purely because of the huge physical gap and isolation between the phototransistor and the diode on this thing. So yeah, my guess is it's they were much better than the dip package. So maybe they just had a higher withstanding voltage than, say, a standard 4N25 optocoupler or something like that. But yeah, I don't know. You'd have to actually get the data on that one. But even your standard optocouplers are pretty darn good. So I don't know. Maybe there's some serious belt and braces happening there. And there you have it. It's not a 1980s vintage, folks. Sorry to disappoint you. It's 42nd week 90. That's probably around about the earliest date code I can find on this thing. The chips seem to be around the 40 or 50th week 1990. So I'm not sure when they actually stopped manufacture on this thing. If you actually know the start and end manufacture dates on the 3457A, do let us know in the comments or on the forum. I've popped the top cover off the processor board here, and you can see the lovely power switch extension bar there going all the way back. I love those extension bars. Great engineering. And there's the backup battery in this thing, lithium battery. Check it out, folks. Made in Britain. Hi to all my British viewers. It's an Eternacell 3-volt battery, and it doesn't look like it's leaked at all. You have to be very careful, by the way, when you're opening these things, servicing them, prodding and poking around in these things. Don't short out that battery at all, and don't replace it with the power off, because you will lose all your calibration data in this thing. So I'm going to check the voltage on this, make sure it's still good. Now, make sure I don't have my meter set to amps, because that would be really embarrassing. I'd short out my battery and I'd lose all the fantastic calibration and the bang-oniness, if that's a term, I'm going to invent it, of this thing. So let's have a look. Ta-da! There we go, 3.06 volts. Beautiful. I'm not going to touch that sucker. Now this is interesting. This processor board seems to have been manufactured at a different time, 4 years prior to when the ADC board. Most of the 74HC chips on here all seem to be dated 86. Look at that, 40th week 1986, 44th week 86, all within the same, all within the same order. 23rd week 86 up here. So almost every one of them. So that is weird. Why that processor board was clearly manufactured, around 80, well, I'm presuming around 86. Otherwise, they bought an absolute buttload of these chips back in 86 and they were still using them 4 years later. I don't know. It doesn't, it doesn't wash. I mean, all of them, the Intel processors, all these chips, all around 86, whereas all this board over here is all 1990 vintage. I mean, check it out. Even the system ROM has a date code of 5th week 1987. My guess is, well, this is a 1987 vintage instrument, but it's had a complete upgrade of this board in 1990 or so. That's the only conclusion I can come to. Now, this is really interesting. Check out all of these dip parts around here, including this part here on the voltage reference board here. They're all got 1826 dash something. Full 5 linear tech parts there, plus National and TI, yet they've all got that same 1826 dash and then a number like 1382 and 0521 and 1265 and all sorts of stuff. So it looks like HP have had these sort of like custom branded. They're, of course, off-the-shelf parts. They aren't like custom chips. They're just regular off-the-shelf parts, but they've had them rebranded, possibly with the HP part number. Now, one thing you won't find in a precision instrument like this is a cooling fan. Why? Well, it doesn't generate a huge amount of heat. I think this thing's rated for like 30 watts maximum consumption or something. It could be a lot less than that in actual power draw. But because when you have a cooling fan in there and it's sucking air through the side vents, for example, in a typical product and then going out, well, you're creating thermal gradients within the product and over the parts, in particular the voltage reference down here, which we'll take a look at, and other parts of the board. And you don't want thermal gradients, because if you've seen my thermocouple video, you'll know that basically any dissimilar metal junction within this unit, any junction at all, solder and copper clad board and everything else, creates dissimilar metal junctions acting as a thermocouple. So you're going to get EMF voltages generated in the unit. So the last thing you want in something like this, you would rather have it heat up to a warm temperature and stay nice and even than try and cool it down with the airflow through the thing. And we can demonstrate this. Alright, what I've got here is my resistance standard hooked up to this thing. It's close enough to 10k here. So this least significant digit here represents 1 ppm of that 10k, so 1 parts per million. And, you know, this thing, Tempco is incredibly low, in the order of like, you know, parts per million. So any, change in temperature in here can actually generate small EMF effects, which can affect, or thermocouple effects in the joints, or a temperature gradient across components that can actually affect the reading when you're talking down in this region. Now, I can wave my hand around in here, so it's not noise pickup or anything like that. Okay, so what I'm going to do is actually breathe on the circuit in here, and you should see this significantly change. Let's give it a go. Look at that. There you go. That's changing by like hundreds of ppm. Look at that. Hundreds of ppm just by breathing over that circuit there. So that is a really big deal for a 6.5 digit precision meter like this. So that's precisely why you won't find a fan in a precision bit of kit like this. You do not want all that air blowing over and creating those temperature differentials across your component. It's a big no-no. And if you take a look at the processor board down here, somebody's actually texted on the serial number for this unit, 2703A 11838, and then a date code in 93. So something, and some other numbers there. So something was done to this thing in 1993. I have no idea what. That is a couple of years after or 3 years after the 1990 dated chips on the analog board. As for the main board here, we have more HP custom part number branded chips. Here's the main processor U601 here, and it's some sort of Motorola part, but it's got this 1820 2624 part number, and that looks like a HP part number. Like here, these resistor networks, look, these are all 1810 and 1820. You'll also find down here, check this out, here we go, here's a national part, 1820 as well. Here's another Harris. I think that's a Harris part down here, 1820. There it is again. That, I believe, is the keyboard, front panel keyboard controller, because it goes down to the ribbon cables to the front panel, or the LCD. Sorry, the LCD's got its own controller, but yeah, they got these freaking custom part numbers on them. Real pain in the ass. And here's the schematic, which I'll actually link in the notes below, so you can load up the PDF of the service manual. It's got the full schematics in here. They're a little bit hard to read, but there's the main processor U601 there that we looked at. And then, of course, it's got, the RAM and ROM. It's all very traditional stuff down here, all miscellaneous control stuff. We've got the speaker down there. Nothing really majorly important there. And then, yeah, here's an extension of it. It's one of these big long schematics, so it's got to be broken up. And then we've got our HPIB slash GPIB controller stuff around here. We've got the non-volatile RAM control. There's our internal battery there, so you can see how that just continually powers that. It's just diode ORed there. And there's the right calibration lock circuit as well, watchdog timer. It's all there, all pretty basic digital stuff, but what that actual Motorola processor is, I don't know. One of the Motorola 8-bit processors, most likely. And then we have our optocoupler link between boards, and that's what we looked at down below. That's at, there you go, it's just serial in and serial out data connecting the two boards together. And of course, this analog board over here actually has its own control processor, and there it is. That's an Intel 8051 microcontroller. And look at this national device here. That's actually, don't know if you can hear that, but that's actually not plastic or anything. That feels like and sounds like ferrite. So they've surrounded all of the leads on this chip here, kind of like maybe as an afterthought, that they've put like a little, effectively, a little ferrite bead through each one of the leads on that national semiconductor device. I wonder why. And of course we don't know what the bloody chip is, because there's another one of the stupid part numbers, 1820-3174. Grrr. And here's another device down near the input down here. What the hell is this doing? This is an 1820-3861. Oh man. But thankfully, of course, you can pretty much tell what that's going to do based on the proximity of these relays. I don't see any discrete transistor drivers for all these relays down here, so that's probably a relay driver chip. And if you have a look at the schematic, ta-da, there it is, relay control U121. And you can see a whole bunch of catch diodes there, which are the get the back EMF of all the switching coils. But basically all of these relays, they're going to be used for not only switching the inputs, but used for the test modes as well. They can short the inputs, they can disable them, and route them through to other test signals, because this meter has a fairly comprehensive built-in self-test. So this 8051 microcontroller, it basically, you know, it does the relays, it handles the optional input switching card, which sits on the top, and basically handles the ADC as well. And there is the custom hybrid ADC in this thing. This one ain't off the shelf by the looks of it. So there you go. I have no idea what that ADC is. It's a, you know, some sort of maybe HP custom hybrid ASIC ADC or something like that to get the performance. I don't know. And here it is, U511. That's the hybrid looking custom ADC thing there, or with it, you know, that's the entire AD converter circuitry around here. And you can tell, you know, we really start getting into precision measurements here. We've got guard nodes marked around here, matched transistor, matched JFET transistor pairs and stuff like that. And here's our reference board over here. That's got our reference Xena on it, and we'll take a look at that. But yeah, that ADC is of course clocked and controlled via the 8051 processor. And here's what a lot of people want to see. What is the voltage reference used in this thing? Well, this is the PCB assembly here. This one is obviously the reference Xena diode with a built-in heater too, of course, but it's a linear technology part. But once again, that custom HP part number, 1826-1249-5, with a date code of the 36-week 1990s. And once again, we've got another linear technology part over here, but once again, HP part number branded, but that's just a precision op amp, clearly. So there's, you know, there's nothing else going on there. And it generates the, I believe, plus minus 10 volt reference voltages, which we should be able to measure on those two test points, I'm assuming. And I'll just verify that. I'll just probe. I assume that that nut there is ground. So I'll just probe that. Yeah, minus 10.175. Of course, it doesn't have to be precise because the, and of course it's exactly, there you go, the positive is the exact opposite of that. So it generates plus minus 10 volt supplies, and they don't, of course, have to be spot on, because this thing compensates for that with the calibration values in the software. And of course, the key to an instrument like this is not its absolute accuracy. As I've said before, that voltage reference down in there, it can be plus minus 5%. Absolute accuracy. You don't care. What you care about is the temperature coefficient, i.e. the drift per degree Celsius. How many ppm per degree Celsius drift? Is it 100 ppm? Is it 10 ppm? Is it 1 ppm? You know, really precision stuff like used in, say, the 3458A, for example, one of the world's best multimeters and the big brother to this one. Well, it's not about its absolute accuracy. You can just trim it to anything you want. It's all about the drift. Now this reference board here, as I mentioned, the designator is A25, and it's exactly the same HP part number as the one used in an earlier model, 3456A, which we do actually have the schematic for. And here it is, the A25 reference board 03456666525, and that's exactly the same part number as what's used in this 3457A. And as you can see, the same 4-pin device here with the internal heater like that, and there's the internal Zener diode, and of course it amplifies that. And of course there's not much to it. It's all about the stability of the Zener diode itself. You know, very carefully selected, very carefully tested and characterized for the performance in this thing. And you know, there's nothing else on this board. There's 1, 2, 3 resistors and a cap, and that's exactly what I see on this board, 3 resistors and a cap. So it's an identical board. And the service manual for this instrument gives U500 listed as an LM299H, and that's the classic National Semiconductor reference. But the one we've got here is a linear technology, but it's still 4 pins. And in case you're wondering, it also lists U501 here, which is just an LM301. Now it's hard to actually get in and see under there, but I can actually see it, and this is actually a 4-pin device. So clearly 2 of the pins are for the Zener diode and the other 2 are for the heater. And you can see there that we're measuring, you know, roughly like 42, 43 degrees or something on that chip. The laser's not directly on it because there's an offset there when it's up close, folks. So I haven't let this thing warm up to temperature, but you know, if you move it to the side, you can see that that is obviously got a heater in it to heat up the Zener, and that would be temperature controlled as well to keep that at a constant temperature. And if you have a look at the input terminals down in here, yes, they are just wired directly across like that, but they do go through a toroid filter. They're wrapped around in there, quite nicely heat shrunk down in there, and then they go directly into the relays. But because this thing is all metal, grounded, shielded, stuff like that, you can get away with those effectively quite long leads going from the input terminals. And there's a 1.1 ohm high value resistor. That's most likely our input current shunt resistor, and you'll notice all the star grounding branching off from that point. It really is quite nice. And this board mounted on top here, this is the AC converter board. It's doing all the true RMS stuff and AC conversion. A couple of switch-in relays and those adjustments which we saw in the top, through the top metal can. And yes, we've got more HP part numbers. Look at that, 1826 there, 1826 up there for that analog devices part, and more of them all the way up the top. HP part numbers as far as the eye can see. And if we pop that AC converter board out, there's only 2 wires levering that thing on. Nice silkscreen designators all on the bottom there, component designators. That's also got its own metal shielding can, so we should be able to remove that. And whoa! Hello! And looky what we have here, folks. We have a whole bunch of well, at first glance you go, whoa, what are they? They don't look like the other relays, but of course Koto is a dead giveaway. Koto is a very high quality manufacturer of precision low EMF read relays and stuff like that. So these are 0490-155. Haven't been able to find the exact data sheet for that one on a quick glance, but they would, yeah, be some sort of maybe shielded or low noise, low EMF relay or something like that. But we've got ourselves a hybrid, and we also have ourselves a genuine bodge. Check that out. They've even heat shrunk the leads. Look at that. Beautiful. And a look at our schematic, folks, reveals all U101 is the input hybrid board there, and it's got all the switch in. Look at that, all the FET switch in required for all of the input circuitry, because here's our input circuitry over here, and here's the input circuitry here. There's some ohms over voltage protection there. Here's all our input relay switching stuff. There's our input fuse by the looks of it, and various range switching stuff. So like you can sort of equate that to, say, similar to like a Fluke custom input switching hybrid that they use in their multimeters, for example. So that's all on that one board, and that would be very well matched. And then of course the output of that goes into these matched transistor pairs here, precision op amps, and various other stuff. So you can, take a look at this schematic until the cows come home. But there's the ohms current source, for example. Great stuff. There's the input amplifier, which I said, and there's the matched transistor pairs. And then we've got a pre-charge offset circuit, and an offset DAC as well. Now that certainly is a very interesting hybrid board indeed. Obviously all the circuitry's on the bottom. They've just got this big ground plane on the top here. There's only one extra trace on there apart from the ground, and it's actually held in by these two screws, and it looks like they just press into those pins, those gold plated pins sticking up from the board. So I should be able to undo those and lift that board off without any damage. Well, sorry folks, that's not the least bit exciting. It's all encapsulated. It looks like it's got epoxied in. You could probably, if you wanted to ruin this thing, you could take off the epoxy or break through the epoxy on the outside of that, and then have a look at the hybrid under there. But of course I want my unit to work, so I'm not going to do that. I'm just going to put it back. And we've got ourselves a little metal can Burr Brown package down in there, and the obligatory trim pot. Now there's one thing I don't particularly care for on this AC converter board, is that it's only held down by that one screw there. I mean, the board does go through over here, but it's not like it's really held in place with that at all. So there's only, I wouldn't like to know about the vibrational modes set up during transporting that thing. I'm not impressed by one mount like that at all. So there you have it. That's about all she wrote for the HP 3457A. Sorry, I just can't go into more detail on some of the chips. I could try and reverse engineer some of them, figure out what they are, but really, it's tough when they brand the things with just generic HP part numbers. Real pain in the ass. Anyway, if you want to take a look at this thing, the service manual for this, which has the full schematics and everything else in it, will be linked in down below. And if you know what that voltage reference is in there from Linear Technology, please let us know. I'm sure there's a lot of people into, precision references on the forum and stuff like that, and they would love to know that sort of thing. Maybe it's obvious, I don't know, I just haven't looked hard enough. But anyway, if you want to discuss it, jump on over to the EEVBlog forum. That's the best place to do it. And if you like Teardown Tuesday, please give it a big thumbs up. Catch you next time.